Hey, welcome to video 13.1. This is really the only video that corresponds to chapter 13. And yes, chapter 13 goes better with chapter 11 than it does with 12. And we're really only doing about half of chapter 13. And it's one major idea, equilibrium. The idea that when things are not moving, and there are two kinds of equilibrium. Translational equilibrium, we already know all about. What that means is the net force is zero. And usually that's going to be in 2 or occasionally 3 dimensions, but basically the idea is the sum of the x forces equals 0, and the sum of the y forces also equals 0. But there's an additional requirement, which is that the system be in rotational equilibrium as well, so it's not rotating. Translational equilibrium says it's not moving up or down. Rotational equilibrium says it's not rotating. And that means the net torque equals 0 as well. And the really interesting thing about this is that the net torque will be 0 regardless of which point you pick as the pivot. Generally, we're going to pick the pivot point to be the point of application of as many forces as possible so that they don't produce torques. But it really is up to us, and one thing you'll get good at if you do enough practice is picking that pivot point. And so if we've got an object at rest, it will satisfy both of those criteria, which means we're generally going to get 3 different equations. And we'll be able to solve for 3 different variables if we want to. Now, in the process of this, we're going to draw something called an extended free body diagram. Instead of treating the object in question as a dot, we're going to draw it more or less how it looks, and the point at which each force is applied really does matter. So the classic example is a ladder leaning against a wall. So here's the wall, and here's the ladder. And the forces acting on this, well, first off, the obvious ones. There's the weight, mg, and the weight is going to act for a uniform ladder at the center. And so the point at which the weight acts at the center of mass. And some other forces. We've got a normal force from the floor there, I'll call that N1. We've got another normal force, N2, from the wall. We can also identify that there is a friction force, F1, from the floor, and a smaller friction force, F2, from the wall. And those are all the forces that act on the ladder. And then if we want to define how far they are, we know that this distance is L over 2, and that distance is L. So that is an extended free body diagram. It's a little bit trickier than a free body diagram, but all in all, not too bad, at least not in the problems you're going to see. And so now we'll actually make that an example. We have a ladder of mass m and length L leaning against the wall. Coefficient of static friction between the ladder and the floor is mu. And we want to find the smallest angle theta at which the ladder is stable. The idea being that as you decrease theta, what happens? You're moving the bottom of the ladder away from the wall. It gets less stable, and at some point, the ladder is going to slip down from the wall, and whoever's climbing on it is going to get hurt. So what we need to do are draw all the forces. So we have mg, we have a friction force there, we have N1, we have N2, and to make this problem easier, we're going to ignore the friction between the top of the ladder and the wall. In practice, that is a very small force and isn't particularly important. Now, we have, remember, 3 principles we have to use. The sum of all the x forces equals 0. the sum of all the y forces equals 0, and the sum of the torques equals 0. Now getting the sum of the x and y forces in this case is incredibly easy. If we look at the x forces, well, we have N2, and we have the friction force, and those together add to 0. And in the y direction, we have N1 and mg equals 0. So nothing terribly interesting there. However, the torques, that's the interesting part. Now, what we're going to do is we're going to pick the pivot point to be the bottom of the ladder. And the reason we do that is that in this case, the torque due to the friction force and the torque due to the normal force 1 are both 0. And that makes this simple. So this sum of the torques, this is the torque due to N1 plus the torque due to N2 plus the torque due to friction plus the torque due to the weight. All that equals 0. But if we do it this way, the torque due to N1 is automatically 0. The torque due to friction is also automatically 0. It simplifies it a bit. Now, if you recall the definition of torque, torque is Fr sine theta, where theta is the angle between the r vector and the friction force, or and the force in question. So the angles we're interested in are this angle here and that angle there. Now this angle here that mg makes with the r vector is theta plus 90 degrees. And this angle here is 180 degrees minus theta. So you've got to do a bit of geometry here. You've got to be clever. And let's start with the torque due to N2. Well, torque due to N2 is the force N2 times the distance from the pivot, which is the length of the ladder L, times the sine of that angle, 180 degrees minus theta. And the torque due to the weight is the force mg times the distance from the pivot, L over 2, times the sine of the angle there, which is theta plus 90 degrees. And notice also that while N2 tends to make the ladder want to rotate clockwise, the weight makes the ladder want to rotate counterclockwise, so one of them has to be negative. And we'll set that equal to 0. And at this point, you can kind of see where this is going to go. Notice we can divide the entire equation by the length of the ladder, and that tells us the length of the ladder isn't going to matter. It's interesting. We can also do a little bit of trig and say, wait, sine of 180 minus theta is just cosine theta. No, it isn't. It's sine theta. Sorry. See, I occasionally forget easy math things too. And then over here we have mg over 2, and sine of theta plus 90, that's cosine theta. So that just got a little bit simpler there. And then we can say, oh, well, this equation here, we get friction in there. So we get f sine theta minus mg over 2 cosine theta equals 0. But definite friction equals mu n1. So we have mu n1, and n1, of course, is mg. And that gives us mu mg sine theta minus mg over 2 cosine theta equals 0. M and g can be divided out of the equation, which tells us the mass of a ladder and the gravitational acceleration don't matter either. And a fair bit of algebra is going to leave us with tangent theta equals 1 over twice the coefficient of friction. And that means that theta equals the inverse tangent of 1 over 2 mu. And there we go. So lots of algebra, fairly simple physics. The most difficult part is writing out the equation for the torques, but that's only because you're not used to torque yet. Once you get used to the idea of torque, this will become almost second nature. And we'll do another example, because that's really the best way to learn this. And this is problem 23 from chapter 13. There's a diagram on page 291. I'll copy it. Here we have a wall with a pivot and a wire. And this angle is 30 degrees, and that angle is also 30 degrees. And the weight of the beam, whatever it is 222 newtons. So what we want to do is find the tension in the wire, then we'll find the horizontal and vertical components of the force from the pivot. So now let's draw the forces. Well, we have the weight force mg, which is 222 newtons, that acts at the center of the beam. We've got a tension force that acts at the end of the beam. And we've also got some force from the pivot that I'm just going to label F, and we really don't know magnitude or direction of that force. So the first thing we'll do is we'll find the tension in the wire. And I've worked this problem, so I know this, but the best way to do this is to start with the torques. So we'll make the pivot be there. The reason we do that is that way, the fact that we don't know this force from the pivot doesn't matter because the distance is 0. So the sum of the torques equals the torque due to F plus the torque due to the weight plus the torque due to the tension, and that equals 0. But when we define the pivot to be where we sum the torques around, that goes away. Now the torque due to the weight is going to be the weight force, mg, times the distance, which is L over 2. We don't know the length of the beam, so I'll just call it L, times the sine of what angle, though? And the angle we want is the angle between R, between the beam and that. So that's 60 degrees. And the torque due to the tension will be negative because it tends to make it rotate in the opposite direction that the weight does. And so that'll be the force T times L, the distance from the pivot. Now the angle we want is this angle here, which I think you'll see is 150 degrees. And that all equals 0. Now fortunately, L divides out of the equation. We know mg, we know the angles. Some algebra gives us T equals mg sine of 60 degrees over sine of 150 degrees. Mg is 222 newtons. We're told that in the problem. And so the tension works out to be 192 newtons. So that's quite handy. Not too hard. As long as, of course, not too hard if you know how to go about starting it. If you're not sure how to start it, it gets a little more difficult. Now, the part B, we need to find the horizontal component of the force of the hinge on the beam, and then part C will be the vertical component. For this bit, it's going to be a little bit easier if we just make a regular free body diagram, so we have fewer angles to deal with. We've got mg, we know that's 222 newtons. We've got the tension force that points in that direction. We know that it is 192 newtons now. And then we've got some force F that we don't know that points off in that direction, sort of. And we'll just use our regular XY coordinate system. That angle there is 30 degrees. We don't know what angle F makes. So we'll do our usual X and Y components, mg, T, and F. Now we don't know F, so I'll just call those X and Y, or Fx and xy, that'll make it a little bit easier. X component of mg is 0, Y component is negative 222 newtons. To get the components of T, that's not too terribly difficult. T we know is 192 newtons. That angle is 30 degrees. So its y component is positive 192 cosine 30 degrees. And its x component is negative 192 sine 30 degrees, which is, and so then we sum all the x components, so fx equals that unknown x minus, that works out to be 96 newtons, equals 0. And so we say that the x component of the unknown force is 96 newtons. That was easy enough. I mean, once you find the tension, this is just a good old-fashioned physics B dynamics problem. And last of all, the vertical component. Sum all the y components, that equals Fy minus 222 newtons plus 192 cosine 30 degrees, all of which equals 0. Doing a bit of algebra and then plugging into the calculator gives us Fy equals positive 56 newtons. So all pretty straightforward. Complicated. But if you remember to work it in steps, you get the sum of the torques, the sum of the forces in the x direction, the sum of the forces in the y direction, it's not so bad. Now what I'm going to be checking tomorrow are questions 3 and 6 from chapter 13. Although at this point you should be able to do all the chapter 13 questions and problems, not that there are that many of them.